Okay, are we on? Okay, great. What we want to cover today is pick up off in the last session dealing with polynomials. And a number of you were absent. I would suggest that you come into the Resource Center and watch DVD, check out a DVD on Friday, the last class session. What I want to do today is spend a few more minutes on polynomial modeling, and then we also need the understanding of polynomials to then start to talk about a new kind of function called a rational function, which is real simple to remember what it is. The root of the word here is ratio. It's a ratio of two polynomials. It's a ratio of two polynomials. So we'll get started on those today after we've done a little bit with polynomial modeling. So what I'd like to do is to begin with using the calculator and taking some data out of a problem in the book, and I'll just verbally describe what the data represents. So if we look on the overhead with the calculator here, you'll see I input, and we've talked about how to input data previously using the statistics features of the calculator. So what I did is I input two data lists. And I believe my numbers here may have started wrong. Let me go back to data set 1. No, actually it's okay. The numbers 1 through 8 are in data list 1. And then over on the right side, in the second list, this is the, I'll just read it to you. In 2005, Hurricane Katrina struck the Gulf Coast of the United States, killed almost 1,300 people, causing almost $200 billion in damage. The following data represents the number of major hurricane strikes in the United States, which are category 3, 4, or 5 earthquakes, each decade from 1921 to the year 2000. So these represent the first decade of the 20th century, second decade, 1920s, 1930s. I'm sorry, this would be the 1920s, 1930s, 50s, 60s, 70s, 80s, and then the last one, number 8 down here, would be the 1990s. And then over here are the number of major hurricanes of higher level category. So this is a set of data that's collected. Now, what we want to do is generate a what using this data? A scatter diagram. And so the way we do that, again, is you have to look at your data, you have to look at your data set, and you build a viewing window in which to see that data. So we'll set a viewing window from, say, -2 to 10, because the data for the decades went from 1 to 8. So I always want to be a little bit outside of those margins. And then I'll go ahead and put a tick mark every 2 decades. And then vertically represents the number of hurricanes in those higher category hurricanes occurring in each of the decades. So those numbers ranged from, it looked like 4 to 10. So I'm going to go from minus 3 to 12 and put tick marks every 2. Now I go to y equals, and I already have, notice at the top here, the stat plot number 1 turned on. If I go to the stat plot command on the y equals key by shifting and going, you'll see that plot 1 is turned on. And I'm going to go ahead and go into it so you can see the details. You have to make sure that's turned on by hitting enter. We want this represents scatter diagram. And then it shows that our x data is stored in L1, the y data is stored in L2, and the kind of marks for our scatter diagram are going to be little boxes. So that's what we want set up. We hit graph, and there's a scatter. Now you look at this data, and it does not look linear. It does not look like a parabola. It doesn't look quadratic. So what we want to do is try modeling it with a higher order polynomial. So what we're now going to do is go to stat and go over to calculate, and then we look down the statistics calculation opportunities, and you'll see here's a linear regression. We've used that before. Quadratic model, which doesn't look like it would be too good. Here's a third degree one, and here's a fourth degree one. This is an x cubed kind of modeling, and x to the fourth kind of modeling. Let's see what else is down there. Let's move down, see what comes lower. Oh, this is a different kind of linear model at the bottom here. This is called natural logarithm curve fitting. We'll get to that kind of thing later in the course. Exponential type of behavior. And then a type of model, power function model. So which one might you select based on that scatter diagram we saw? Cubic seems like a logical one. So if we go ahead and select number 6, so I'm just going to punch number 6. It puts this on the screen, and then I should specify, it'll understand L1 and L2, because that's what people are normally using. But if you wanted to, you can specify the list names here, and those are found on your numbers 1 through 6 keys on the calculator. So you could go L1, use the comma key, which is up above the number 7 key, and then followed by the list number 2, which is on the number 2 key. And so you'd have it do the calculation, and then what you want to do is write these numbers down on your paper. So you'll notice here's the general structure that I talked about last class session for a cubic model. And these coefficients are constants then shown here. And so you'd write those down, and don't worry about the R at this point in time. It has to do with the how good of a curve fit the model is. It's an indicator of how good the curve fit is. So if you have those then written down in your notes, and you've got yourself the window settings and a little box with a drawing of the scatter diagram, then what we can do is we come back to y. We find an open spot here to place the function, and then anybody remember how we can get the function with all its accuracy in here without having to punch it in by hand? You go to variables, the variables key, which is near your blue arrows, and you go to item 5 for statistics, item 5 for statistics, and then you come across the top here, arrow keys to equation, and there it is, it's hidden. It's buried inside this menu under the variables key. Variables, statistics, and then come over here to equation, and here's the regression equation tucked in here. So I now punch number 1 and watch what happens. It now takes and puts that entire equation with all its decimal accuracy, that cubic, you can see the cubic polynomial right here, and then we hit graph, and it now lays the curve of best fit, the cubic curve of best fit, over that data set.
So why did we need to write it down if it's going to be, if we're going to just pull it up there?
Well, you have then a little bit of a written record, and probably round off to a couple decimal places on the coefficients. That way, at least you got a written record in case your batteries die or something like that. You don't have to go back and reinvent the wheel. Okay. Or if you're turning to me for grading purposes, okay, great. Or if you're turning a report in to your boss on the job where you've collected some data, no matter what the application might be. You're not just going to say, oh, here's the answer. You're typically going to have to show what your rationale and how did you do it. So just like on a job, the same kind of a reporting technique going on. So this looks pretty good. So now what's really nice about this model is if this is a prediction over the 20th century to the year 2000, then what we could do is we could say, okay, let's come out here. Let's see, this I guess is going to be the year 2000, right here where my pen is marking, roughly right there. So here's this data set. So if we turn trace on and go to 8, whoops, trace. Let's see, trace back here. I'm going to just come across here. You can see the data set. So it looked year 2000, from the last decade of the 20th century, 1991 to the year 2000, it looked like there were five major category 3 to 5 hurricanes. So what we could then do is we could then make a prediction now using this model. And so what I have to do, notice I'm on the scatter diagram data set. So I can't get anywhere other than on those data points. So what I now do is I use my down arrow or up arrow key. It now jumps me onto that model. You can see it up there at the top of the screen. And so now what I could do is I could come in here and I could pick a decade that is outside of this set of data. So I could extrapolate to, say, the first decade of the 21st century, 2001 to 2010. So what I could do then is put in a what number for x? I put 9 in because the data set was 1 through 8 from the decades from 1920 through the year 2000. So I'm going to put in a 9, and we would predict we're coming back up. You can see the cursor right here. We're coming back up. It looks like possibly predicting maybe 10 significant hurricanes in the first decade of the 21st century. Okay, so that's one simple way of doing some polynomial modeling. Notice that the characteristics we talked about last class session, this looks like an upright, down left cubic function. If I lowered this graph down, how many zeros could it potentially have? If I brought this graph down lower, where the x-axis went about where my pen is, you can see that the zeros would occur 1, 2, possibly 3 times. How many turning points does a cubic have? Remember what a turning point is? A turning point is where a function changes from increasing to decreasing or decreasing to increasing. So here we have a transition from increasing to decreasing. There's a turning point here, and there happens to be another turning point here where it changes from decreasing behavior to increasing behavior. We talked about all these items in the last class session. All right? So that's polynomial modeling. We could have done, let me do real quickly with you. Let me erase that model, and let me go back here on the home screen, clear, and I'm going to go back to statistics, and I'm going to go to calculate, and I'm going to pick a 4th degree model down here, item number 7 this time. I'm just going to do it real fast. This is a 4th degree model. You can see the polynomial laid out for us on the top there with its coefficients. And then I'm going to go to y equals, and I'm going to stuff the 4th degree model in here now. So I'm going to go to variables, item 5 statistics, over to equations, select number 1, it's in there, hit graph. Here's the 4th degree polynomial coming up. Looks like a cubic. Does that look right to you as far as a 4th degree model goes?
It's going to go further over.
Okay, if this one is dropping down left and this is a 4th degree polynomial, then this thing has to do, it looks to me like it's cubic, but what's going to happen off to the right? Does this show the end behavior? It's going to have to arch over and come back down for it to be an even powered polynomial, a 4th degree polynomial. So how can I see that? I can increase my width on x, and so all I have to do is increase this maybe, why don't I change it to say 20, get out there far enough, fitting the data fairly well. Looks like there, okay, see what happens? So by you having some knowledge of the polynomial, general polynomial's characteristics, then you know that a 4th degree polynomial in this case would have to be down left and down right to show all of its character. And you can see that it's a little bit better. Let's see what the prediction would be if I went on to that model and picked 9. There it is. This model's only predicting 7 major hurricanes as opposed to 10 in the first decade of the 21st century. Okay, so this is how you do mathematical modeling, letting the technology assist you. Okay, let's go back up on the board now and look at another model that I'm going to go ahead and write up here. Let's do one more polynomial. And this is going to be a cubic polynomial, so I'll just call it c of x. And it happens to be x cubed plus 7x squared plus 6x minus 18. How would you investigate this model? Usually, first of all, you would try to factor it. However, you're really good with factoring quadratic expressions, right? But when you see a cubic, these things oftentimes will not factor. Very tedious hand way of doing it that nobody even teaches that anymore on how to do it by hand, but there is a method. But we don't want to do that. We've spent big bucks for the fancy calculators, so let's utilize it to see if we can get a handle on how to factor this thing. So, let's come back to the calculator now. And I'm going to make sure you turn off on the top there. First of all, I'm going to clear this guy. I'm going to go up onto that plot 1 and hit enter to turn it off because I'm not doing data plotting anymore. I come down here and punch in x, and I could use the math key. If I use the math key on the left side of the calculator, I could pick item number 3, which is cubing. So there's x cubed plus 7x squared plus 6x minus, whoops, that should be subtraction and not the negative sign. So subtracting 18. I'm going to set a relatively viewing window to investigate this thing, and also notice something here. This graph is down 18, isn't it, for a y-intercept? You can see the y-intercepts easy on polynomials. Zero out x, and you end up with negative 18. So you know you better set your window down low. Before you go just letting the calculator do everything for you, keep your brain engaged. Here's a series of power functions added together with a negative 18 on the tail end. So this thing is the one that drives the end behavior. And I talked about this last class session. This drives the end behavior. It's going to behave like an x cubed graph if you get to large values of x. It's going to go up right and down left. These power functions in here are going to cause some adjustment to occur on this crazy thing. Okay, so now I'm going to set a viewing window not too far to the left, say minus 5 to the left, 5 to the right, tick marks every one. But I'm going to go fairly large on this, say minus 25 to 25, and put tick marks every 5. So you jot these 6 numbers down and hope for the best now by hitting graph and see what happens. Okay, does it look like it exhibits the characteristics of a cubic? Now the one thing I'm a little concerned about here is it doesn't really show it dropping off more to the left. So what I'm going to do is come back and reset the viewing window a little bit by going a little bit further to the left. So x minimum, I'm going to make it minus 8 instead of 5, negative 5, and hit graph again. Now I can see those characteristics. Okay, let's come back up on the board for a second. So we had minus 8, 5, 1, minus 25, 25, 5 for the window setting. We had the equation, which you've already written down on the other board. And then we have a viewing window that goes off the bottom of, I usually draw the axes first. And I see where it goes off the bottom, where it zeros, where it peaks, approximately, where its y-intercept and where it bottoms out, where it zeroes out again, and where it goes off the screen. And then I can lay that curve in there pretty nicely. I have a real good sketch. Now what are we up to? We're investigating this particular cubic function, which we call c of x, x cubed plus 7x squared plus 6x minus 18. What could we right away label on this picture? right here, couldn't we? 0, negative 18. Feel good. Now, we're trying to investigate this. This is a cubic model, so it does exhibit all of the characteristics, doesn't it? It shows down left behavior, which it has to have for a cubic, and upright behavior. What's a more formal way, instead of being so casual about this, what's a more formal way of indicating up? If x approaches infinity, if you're going out to the right, in other words, what's happening to c of x? It's going up, isn't it? It's also heading towards infinity. So this is a little fancier way of the mathematics to describe that end behavior. Over here, as x approaches infinity, heading off to the left, you can see on this picture that the c of x values are approaching negative infinity. Okay, so what we've got now here is we have these max, mins, and zeros. Our objective was to see if we could factor this down to find the exact zeros. Exact zeros? Question mark. The exact x-intercepts. So if I look back now on the calculator, let's go back and look at the calculator once again. If I look closely here, I think my tick marks were every one. This doesn't look like it's quite on 1. 1, 2, 3, 4, 5. So what I'm going to do real quickly is you've all learned how to find the zeros with your calculator. Why don't you folks take, if you've got this punched in, go ahead and quickly work on trying to find the zeros. And I'm going to try -3. Me like this might be here at -3 by turning trace on and going to -3. Oh, I lucked out. Look at that. By just hitting trace and guessing -3. Let me go over here and see if -5 works. I'm still in trace mode. No, look at that. It's not at -5, it's positive. So it looks like it's got a 0 that's not on a nice number, but this one's good. Okay, and then how about over here near 1? Does that look good? Let's try 1. Nope. It's negative valued, so if I move over, it looks like there's still negative there. If I move a little further, now it's positive. So it looks like it's a little bit past 1 over here on the right. So back to the board again. We were able to see that -3 works as a 0. -3 works as a 0 precisely. So if x equals -3, then watch this. See, what I'm showing you is how you take a general function that you don't know how to factor and how you can play with it to see if it's factorable. If you can find a nice, clean 0 like this, then notice that x plus 3 equals 0. X plus 3 equals 0, right? So this potentially could be a factor. Now, let's practice long division. And before we do long division, I want to do an arithmetic problem with you because a lot of you probably haven't done long division for years. So, let's see. If we have a fraction, let's say we have 47 divided by 6. This is called your numerator. Everybody's good at that. And denominator, right? And to do long division, we're going to do the following. Now just hang in there with me because it's going to read algebra here in just a second. This is also called the divisor. Divisor and the dividend. this discussion is also going to play into us talking about rational functions that are coming up here in about 5 minutes. Okay, rational functions. So I'm going back through some of this vocabulary with you that you maybe forgot as a kid. Divisor, dividend. 6 does not go into 4, so we try 6 into 47. Goes almost 8 times. So it goes 7 times, multiplying the dividend, the quotient times the divisor is 42. We take the difference here, bring down this 5, and then we have a decimal. Actually, I'm going to leave it that way. This is now, 6 does not go into 5. This is the remainder. And so what we end up with here is a mixed number, 7 and 5, 6, as a mixed number. Right? Old school. Watch this. We now are going to see if x plus 3 divides into this cubic function. X cubed plus 7x squared plus 6x minus 18. Take notes, unless you already know how to do this. Similar to what we did with the arithmetic, x divides into x cubed how many times? X squared times. Now you multiply this quotient value times this, and we get x cubed, and then keep going. X squared times 3 is plus 3x squared. Now, what did we do back here on the arithmetic problem? Back on the arithmetic problem, we then mentally subtracted this from that and was left with 5. We do it similarly here. Don't go in here and start changing signs. Mentally subtract this from that. This then becomes negative, and it cancels out with that. This becomes negative to that and leaves you with how much? The difference between 7x squared and 3x squared, the difference is positive 4x squared. Now we bring down, usually we're going to be bringing down like you did in long division. We're going to bring down 6x. And now x goes into 4x squared. How many times? 4x times. So we get now 4x squared plus 12x. We mentally subtract this stuff where my hand is. So we lose the 4x squareds. This becomes a negative, right? Negative 12x added to 6x is negative 6x. Bring down the minus 18. And now x goes into negative 6x, negative 6 times. Multiplying, we get negative 6x minus 18. And take this material away from the binomial above, and you lose the x's and you lose the 18s. You get a remainder of 0. Yes?
Like terms over like terms, like the x squared?
I thought I
the
did.
X squared?
Well, no. Just like back here in arithmetic, where do you put this quotient? You put that quotient above that last digit that you were operating with. Okay? Everybody okay? I believe there's some homework assigned on practicing long division. So this is a quick review. If one of these terms was here originally, like if there was no 7x squared in our polynomial, folks, and you wanted to try long division here, what you would do is put plus 0x squared there as a placeholder to keep your division working properly. So if there's a missing term, you put 0 as a coefficient times the power, the appropriate power function.
And there's a remainder you add to whatever you add.
Yeah. Yep. So now, what is very exciting here, I don't know if you're as excited as I am, but let me erase the arithmetic. This tells us then, by getting a remainder of 0, that this divisor times this quotient is equal to that polynomial. So our c of x is x plus 3 times this quadratic quotient. Now look at what the original question I posed was up above here. What exact zeros are there? What exact zeros are there? And so we were able to see that this thing factored into this real nice form here. And so we know right away, by having used our calculator earlier, that -3 works. So here's the factor. And this is now quadratic. And you folks are fast solving quadratics, aren't you? Okay? So what we would do is we now need to solve x squared plus 4x minus 6 equals 0. And we could use the quadratic formula, right?
How do you know which one?
What do you mean, what to pick?
Quadratic or completing the square?
Oh, either one. Completing the square always works. Matter of fact, let's complete the square just because we're getting real good at it and we don't want to forget it. Okay? So x squared plus 4x, half of 4 is 2. We've done this several times in class now. We tuck the square of that in here, plus 4, and at the same time I'm going to move the -6 to the other side as a +6. Now I completed the square here on this expression on the front, x squared plus 4x. I completed the square, but I need to add 4 over on the other side to keep things balanced. And so then this is x plus 2 quantity squared equals 10. And finally, x is then equal to, move the square root both sides and move the 2 over, and you get -2 plus or minus square root of 10. -2 plus or minus square root of 10 for the exact zeros. Back up to the graph. We then can label our graph with its zeros exactly. -2 minus square root of 10, comma 0. Its value, folks, this is -2 minus, and isn't this number a little bigger than 3? Square root of 10 a little bigger than 3. So we're taking a number a little more negative than -3 away from it. See how I use that little negative exponent there? And so the sum of these is a little more than -5. A little more negative than -5. Mentally. The other one is right here. And this one is at -2 plus the square root of 10, comma 0. Exactly. So here are the exact zeros. And this is -2 plus a number a little bigger than 3. Take 2 away from a number a little bigger than 3, and you get a number a little bigger than 1, don't you? I wrote years ago a quadratic formula program that you're welcome to come over and I'll download into your calculator for you. So let's come back to the calculator screen and watch how quickly I can confirm this. So what I can do, I can quit here, and I can go to Programs, and I can go up arrow on my list of programs, and I have quite a few in here. Oh, you know, this calculator might have the old program in it. Let's see what it's got. If I run this thing called Quad and hit Enter, it lets me enter the ABC values. we are dealing with x squared plus 4x minus 6, right? So I'm going to put in a 1 for a. The b is 4, and then a negative 6. There are the two zeros. So you will notice those values a little more negative than negative 5, negative 5.1623, and the other one was a little bigger than 1, 1.1623. And notice that those values, because of our use of the, look at the algebra here, you go to x equals negative 2 on your graph at negative 2, and then you go symmetrically from negative 2 to either side by square root of 10. So this is how you would invent a polynomial function, in this case seeking the exact zeros. What's the other features that could be asked about in a question like this? What other features could be asked about a polynomial like this? Yes, where are the turning points? And are those turning points either a maximum or a minimum? And you know how to use your calculator to do that. So, or go back to one of the previous class sessions. You can watch it there. Finding this location, that location. Okay? That pretty well covers the concepts in this second session dealing with polynomials. Any questions on this so far? Okay. I've got another question for you, because this is something that's fairly important that people related to the same problem. Where, I'll say it in words and then I'll write down the math, is c of x greater than 0? Where is c of x greater than 0? Let's let somebody else answer. Somebody from the silent majority. Where on the picture is c of x greater than 0? How many of you are sure? Being shy, and that you know. Oh, okay. Well, now what is c of x on the graph?
Y.
It's y, isn't it? It's the height. Right? So if you see mathematics, and that's the reason I was asking this, because I thought there might be some confusion. Here's the question. Where is c of x greater than 0? Okay? So what we're asking is, where is this graph above the x-axis? In here and out there. See it? So when it says where, we want to specify an interval of x. An interval of x where the y values, the heights, are positive. This is very important, and you've seen previously in homework about it. So what you're going to answer here is an interval from negative 2 minus square root of 10, comma, to negative 3. That interval right in there between that 0 and that 0. And you're also going to say out beyond this 0, out to the right 0. So you're going to, interval notation, you're going to be at 2 plus that square root of 10, comma, infinity.
But
So,
not including negative 2, 1 plus a minus square root.
good question. Are you including, do I put square brackets on these things or not? The question says, where is it positive valued? Where is it positive valued? This thing could, over some period of time, maybe here we are at the current time, and maybe this is the last couple years of a business, and maybe this is the profit, like a data set modeling profit. And then the recession hits, right? Realistically, the recession hits. profits are negative for a period of time, and now there's some recovery occurring, okay? So you might be real concerned about where your profits in the business are positive. And you got back in those months, back in there, in that period of time in the past, we had positive profits. Oh, things are looking good now. Okay, this is the kind of thing that you might get a bonus for, okay, if you can do this with your business, okay? Do you see how you can play this with real data? And you build a model similar to the previous one we did, except this might be some real information. Okay, let's spend the last few minutes today seeing this new type of function called rational functions, which are, again, I mentioned earlier, ratios of polynomials, a numerator polynomial and a denominator polynomial. Okay. So rational functions. Let's call it R of x. That seem reasonable? R of x. And we're going to have a polynomial in the numerator made up of a group of power functions, or a constant, and a denominator with some power functions. Why don't I call this numerator function n of x and the denominator function d of x? And I think you can see why I did the little long division problem with you earlier. These are polynomials. Why don't we let's put that cubic we worked with in the numerator, because we knew something about it. We know something about that thing already. So let's take and use that same darn thing. X cubed plus 7x squared plus 6x minus 8. 18, excuse me. 18. Same numerator polynomial. Now we know a bunch about it, don't we? Okay, here's a denominator one. How about 16x to the 4th minus 81? So what we've got is a 3rd degree polynomial divided by a 4th degree polynomial. And I just made this up, so, okay? This would be a general form. This would be a general form. Let's write next to it a factored form. So let's see, the numerator we worked with earlier. And this denominator, folks, reminds you of something we reviewed earlier in the course. A perfect square minus a perfect square. So that thing right off here on the side is going to be a 4x squared minus 9 times a 4x squared plus 9. Right? Are we done? Thank you. Okay, good review, huh? So this difference of squares here could also be factored into, y'all should be very good at this, 2x minus 3 and 2x plus 3. And then don't forget 4x squared plus 9. Is anybody wondering what we want to do with this? Anybody wondering? Factor it? Does not factor, folks. Does not. How many students will write down, how many of you would write down 2x plus 3? Okay, we don't do that. For those who just raised their hand, watch this. What's the square root of 16 plus 9? This number in here is 25, isn't it? Is that 4 plus 3? No. Okay. So sums underneath the radical, you can't go splitting those up, which is the thing to do. So don't ever do that. Okay. So a sum of squares will not factor. Okay, we're a little short of time, less than 5 minutes, so what I want to do is write this factored form down. We have a 2x minus 3, a 2x plus 3, and our 4x squared plus 9. Okay, this is called then the factored form. The factored form. With rational functions, we can see some things from both of these forms. We can see some interesting features. When you do graphing, what is an easy intercept to always to find? And when you have a function, what's an easy intercept to always find? The y-intercept, right? You can easy to find the y-intercept. All you do is what? Make x 0. And notice this rational function, you just put 0 in for x here, and you zero out your x in the numerator and denominator, and all the x terms disappear, right? And you're left with negative 16 over negative 81, right? I'm sorry, negative 18 over negative 81. So you can see the y-int always easily from the original form, the general form. So you get 0, comma, and we have 18 over 81, right? There's a common 9, right, that reduces. So it looks like you're left with 2/9. Is that right? 2/9. Okay, so you always can get a y-intercept easily from this, from the original form. There is one exception to that, and we'll wait till the next session to talk about that. But 99.9% of the time, this is always right off the bat. Now, in the last minute or two, let me just hit one other item regarding fractions, because a lot of people have trouble with fractions. Back to arithmetic. How many times does 13 divide in 0? Think about that. How many 13s go into 0? 0 of them. That's a perfectly good value. Perfectly good value. However, how many times does 0 go into 13? What if this was a real tiny, tiny number? A tiny number, like 10 to the minus 5. Okay? Like a 100,000th into 13. How many 100,000ths are there in 13? A whole lot. A lot, right? So 0 divided into 13 goes an infinite number of times, which means it's undefined. Which means it's undefined. Okay. Undefined. So, in closing, what I want to point out to you is that in the factored form, folks, if you can factor the numerator, you can see the zeros. You can see the zeros of your original rational function. If the numerator function equals 0, that's how you find the zeros. What happens if you try dividing by 0, folks? You have trouble. Domain. We talked about that earlier in the course, don't you? If you divide by 0, you've got trouble in the domain. So down here in this denominator function, d of x equals 0 is trouble at those x locations, right? And so look at this right here in the factored form, folks. You can see that at 3/2 and at minus 3/2, you would zero out that data. So the domain of the rational function would be negative infinity to negative 3/2, and then from negative 3/2 to 3/2, it's okay. But right on negative 3/2, you got trouble. And at 3/2, you also have trouble. But then larger numbers than that are open. So here is the domain of the original rational function. So what we'll do next class session is we will continue on. We'll start over actually with rational functions and illustrate the different details of these, and we're aiming towards being able to get the graph, being able to get the graphs of these crazy things without having to touch our calculator. And then we use our calculator to help us confirm our work. Okay, for today.